This lecture is a continuation of part 1 of core log integration. Please check the YouTube channel to verify the first introductory lecture so that we can move ahead with this second component that is devoted to clastic sedimentary sequences. Thank you. Hello everybody, how are you doing today? This is Professor Carlos Torres-Verdin, broadcasting live today from the famous Bureau of Economic Geology of the University of Texas at Austin, Hook and Horns. And we're here at the core facility of the Bureau of Economic Geology. You can see that we have an incredible array of core samples laid out for us to do our analysis. The room is actually larger than you can see from the view here. We have core samples coming from 3 different wells. One covers a turbidite sedimentary sequence, a clastic formation. Then we have another well that covers a carbonate formation, that is the Outcrop field in the Permian Basin. And we also have a very unique, interesting core sample here that comes all the way from the Eagle Ford Formation, spanning the geological record that goes from the Buda Formation to the Austin Chalk, going through the different components of the Eagle Ford Formation that we're going to analyze to understand the presence of organic material. So it's a very unique lecture because so far we have looked at well logs, like this diagram here, where we have multiple ways to shine physics to the rocks: gamma rays, resistivity logs, nuclear logs, sonic logs. We have also ways to take samples of the rock and take them to the laboratory and quantify properties such as porosity, permeability. So we have all of that. But here in this exercise, we have the ability to compare well logs to core data, to samples where we can actually understand the genesis and diagenesis of the rocks. We can see features that are much higher resolution than the features that we can see at well logs. So this is typically what we want to do. If you have a well that has core and it has well logs, you have to look at the core data, the core samples, before you even begin to interpret the well logs. Why? Because interpretation, as you know, is based on models, is based on assumptions, is based on algorithms, is based on parameters. And all of those parameters, they need to be chosen with geological criteria in mind, so that the interpretation, the quantification of properties such as storage and flow properties, geomechanical properties of those rocks is precise and reliable. So we have to do that. So in cases where you have key wells with core and well logs, you have to do that. Of course, that relationship, that nexus that you have between the two, between the well logs and the core samples, then you can implement to interpret the well logs acquired in wells within the same field where you don't have core data. So it's very important. It's an exercise that is implemented widely by all the exploration development companies. If you are in the geohydrological business, you have to do this. In many other aspects of subsurface resources, it's a very important exercise. So that's what we're going to do today here at the Bureau of Economic Geology, where we have this core facility, beautiful core facility, and we have all this core that was laid out just for us so that we can have an incredible lecture and you can take advantage of this knowledge. And we are going to have a couple of very renowned, famous scientists from the Bureau of Economic Geology walk with us through some of these core samples. So it's a very interesting and exciting exercise. I hope you like it. I hope you enjoy it. Please send me comments and anything that you want to analyze, don't hesitate to email me. With that said, let's just go for it. Let's go for the lecture. Thank you. Hello everybody. Today we are at the Bureau of Economic Geology in one of their core viewing rooms. This is one of the temples of geology, applied geology. People come here to see all kinds of rocks, all kinds of core data. The Bureau has one of the largest collections of core around the world, certainly in the state of Texas, from all kinds of rocks with different variability. They also have access not only to the core, but also to the well logs and core laboratory measurements of these fragments. So today we're going to talk about three wells that have three very distinct types of rocks. We are going to start with a well that has unconventional rocks. This is the Cinco South well that covers the entire Eagle Ford formation, starting from the Buda formation all the way to the Austin Chalk. And then this is walking fast through this piece of rock that has a tremendous variability. The Eagle Ford vertical well that was core. And then we're going to look at the logs of this formation acquired across this same well. We are going to understand the variability of these formations as indicated by the well logs and the tremendous variation on storage flow properties, the presence of organic material, this and this clastic rock. And then we're going to introduce ourselves in the world of carbonate formations and this Permian core sample coming from the Sacroc field in the Permian Basin. And we're going to analyze the variability of carbonate formations, tremendous variability across all of these rocks. It's a feast, a geological feast that will have an analysis of all the different logs, the gamma ray log, resistivity logs, nuclear logs, sonic logs, core laboratory measurements. And we are also going to look at another interesting detailed sequence of turbidite rocks, a clastic rock, and we have all the logs that accompany this sequence, where we have a laminated siltstone, we have presence of laminated shells like we covered in class. Look at these shell laminated sensors of a turbidite system. And then we have also thickly bedded turbidites. We have the core measurements. All of these cylindrical holes that you see here is because they took plugs to analyze them in the laboratory to assess storage and flow properties. And then we have segments that are rich in organic material shells that serve as compartments. And then we also have very interesting features of mud flows. And all of these, interestingly enough, in this clastic sedimentary sequence, look at this degree of laminations. This can tell you where you are with respect to the turbidite sedimentary environment. So those are the cores that we're going to talk about today. How about that? This is going to be a geological feast, an incredible lecture that will take us to the confines of clastic rocks, turbidite sequences, carbonate sequences in the Permian Basin, and the Eagle Ford formation, a prominent shell. All of this through geological time. we are going to understand how these rocks relate to well logs, or well logs relate to them, and how we could use the well logs in key wells that have core data to understand the correlations between rocks and logs, and how to analyze well logs in the context of core. Hello. Now we have a very quick introduction to the features that we are going to look at when doing core log integration in a turbidite sedimentary sequence. It's very important to remember what a turbidite sedimentary sequence is, and I went through this in some of the lectures. That's the geological context. Let me just remind you that these are deep or shallow marine deposits that are formed from avalanches of sediment that accumulate on the shelf and the continental slope that are triggered by mechanical instabilities when the amount of sediment, the volume of sediment increases substantially beyond the condition of equilibrium. This is very similar to snow avalanches that we have in winter time, with the difference that the avalanche of sediment now settles in water, so we're subject to the currents of water, the depth of the currents, and because the avalanche is going into a medium like water, then there's preferential separation of grain sizes. Large grain sizes get together close to the channel, and small grain sizes begin to deposit in large amounts in the distal portion of the turbidite system, which are so-called the fan complexes. And we also have crevasse places here. We also have levees. We also have secondary channels. And please understand that this is just one event over geological time because of the sudden increase of the amount of sediment due to an avenue of, for instance, strong rains and so forth, so on. We can have multiple stack channels like this that are varying laterally and also with depth. Same with the distal fan complexes that we have. So depending on where the well is drilled in these very complex system, we will be either in the distal portion of the system where we have a fair amount of clay and sandstone shell laminations, or we will be in the center of the channel where we have traditionally the largest grain sizes, or close to the levees, or close to the crevasse place where we have a mixture of grain sizes. And all of these variations are going to be the amalgamation of these variations, that is to say the stacking of the channels or the stacking of the features in depth because of multiple episodes. All of those things are going to be shown with very definite marks and distributions when we have a well that is drilled through a sequence, through a juxtaposition of many of these features over geological time. Here is an outcrop that shows the center part of the channel, and in the channel we also have a sequence of interbedded layers of sandstone with relatively minor amounts of shell. So that would be a well going through a channel. And here is an outcrop from France that shows and cut several turbidite channels. Here we have one right here. There's the upper part of the channel. Here we have the boundary of the channel. Then we have another one here, and then at the bottom we have the typical succession that we see in the distal fan complexes, where we have very thin beds and significant amount of shell laminations. We have a few other channels at the top, but this one here is the most prominent in the cross section. So imagine if you have a well that goes through here, and that well is going to, at different depths, cut through channels, through presence of shelf, which are already outside the boundaries of the channel, or go directly to another channel and maybe also intersect a fan complexes that's older than the previous one. So we have these superposition of channels that are cut, or I'm sorry, superposition of features along the turbidite system that are cut by a given well. And because we more or less know how to recognize the location of a particular segment of the well in the context of the geological turbidite system, then that allows us also to have contextual information about the lateral extent of these features. And here's another example of an outcrop. In this part we have beds that are very thin and that are also laminated and interspersed by layers of shell. This, if a well was drilled through this sequence, that would be the distal part of the turbidite system, which is the fan complex. Here's another interesting outcrop that shows the distal part of the fan complex of a turbidite system. And we recognize that because of the very high degree of sandstone shell laminations, where the sandstone and shell layers have very similar thicknesses. So a well that goes through here will be in the fan complex. The lateral extent of this development is typically very large, but the efficiency of the storage and flow will be considerably limited by the presence of shell layers. But even so, we may see hydraulic communication among all of the sandstone layers that we see here. So that's an important property of these systems for reservoir, for geological applications, for hydrocarbon applications. And when we do a closet view of some of these outcrops in turbidite systems, either in the channels or in the crevasse plays, levees, or in the fan complexes, we are going to see the relics, the imprint of the currents of sediment as they settle at the base of their component of the system. And here, for instance, we can see a succession of events of deposition marked by different boundaries, and each of the boundaries has a different trace of sediment action of the water on the sediment that we see here. These are typically studied in what is called the BOMA sequences of turbidite sedimentary systems. Here we have, in this other picture, we have more elements to understand the different currents that take place as a function of different depositional environments on a given sector or portion or element of the turbidite sedimentary system. And on the left here, we also have a very important sequence of shale and sandstones in close succession, which is already telling us that this portion of the rock is in the distal part of the turbidite sedimentary system. So the well logs that we're going to look at in this video lecture, they come from a well that is called Brown Trust. We have some elements. It was operated by Hillier Oil and Gas Incorporated. The features that we have here are all in depth. Here are all the features in depth. We have the gamma ray log. We have the resistivity logs. These are induction logs. There is the super shallow, then medium, and deep resistivity logs. We can see the presence of invasion as manifested in some of these logs. Then we have the neutron density PEF logs, and we have the gamma ray log and the calculated gamma ray log. Calculated in this case means that the component of the uranium part of the gamma ray log has been eliminated. And then we have here the core samples. And all of these core samples are identified by the filled circles, the solid circles. So each one of these, you can count them. And we're going to see over on the core data that each one of these is identified by a plug, the location of a plug. And so the coring interval began at 7,660 approximately feet below the Kelly bushing and ended at about 7,700 on this close-up view that you see here. Please remember that the sampling rate of some of these logs is anywhere between half a foot or 1/4 of a foot. Most typically for wells, this old is approximately half a foot. So samples of logs are taken every half a foot here. Same for all of these. And of course, the well logs by themselves are depth match, but when we have core data and they're placed in depth, they are placed in depth based on a system that has to do with measuring depth while drilling, which is not the same system that is used to measure depth with open hole logs, which is by the length of the cable, the wireline cable, subject to corrections because of tension. So it's a different system with depth, and typically when one places the plugs, the location of the plugs, the location of the core samples in depth, typically we will find a mismatch in depth. Could be either that the entire sequence of plugs is bulk shifted in depth or is shifted at intervals, so something like a stretch and squeeze. And when that happens, we have to, before we begin to do any analysis, we have to be able to depth match these measurements. And typically this is done with the gamma ray log, either by acquiring the gamma ray log in the laboratory of the core samples. There's a tool in the laboratory that we go through the core and it measures the gamma ray log, so it gives us a gamma ray log of the core. And then that gamma ray log of the core is depth matched with the core itself. That's one procedure. Another procedure is if you have the core samples here and you have the grain density and you have the porosity because you did all of these measurements in the laboratory, then one can calculate the density log from core data. It's a density log calculated from the measurements of core data, and then that density log is depth matched with the density log acquired in the well. So there are multiple ways of doing this, but it's very important that we do the analysis, because once you do the analysis and you can see, for instance, that the highest permeability is shown here occurs in the local minimum of the gamma ray log, and we can also understand whether this is the maximum porosity or not. So there are very important features that we can recognize from logs, but those features, they also need to be recognized with core data, and that's the reason why depth matching is such a very, very important endeavor when we do core log integration. And typically also these plugs are selected when we slab the core, and they are selected over important intervals that are significant because they need to be quantified in terms of storage and flow properties to decide on any, for instance, hydraulic communication, any property that is important to assess whether these rocks in their communication with other wells or in primary methods of production will have sufficiently good properties to produce valuable resources over time, cumulative production. And of course, this could also be done for geohydrological applications or for any other application. So that's the reason why core data are very important to match. The other thing that I want to show here from these logs is that precisely the largest, in this example, the largest permeability that we see on this track, this is gamma ray log on this track. Then we have the resistivity logs, shallow, medium, and deep. Please note that in this example, not all the time, when in this example we see differences, that's a very good sign because we have mud filtrate invasion that indicates permeability, but it doesn't indicate the degree of permeability. But when we have core samples and they lay out very nicely with at least the core porosity samples, they lay out very nicely with the density log, in this case expressed in sandstone porosity units, we see that we have a good depth match. And also when we compare to the permeability core samples, we see also that the largest permeability in this example, not all the time, but in this example agrees well with the highest value porosity. Please remember that porosity increases from right to left. The other thing that is very important to understand is that all of these were plugs. We're going to see the core in a minute, but all of these plugs are cut with a particular size. And why are they cut with a particular size? Well, because when they are sent to the laboratory facilities, especially the commercial laboratory facilities, they operate with instruments that are capable of doing a multitude of measurements at the same time, and so they require that the samples be cut with a particular size so that they fit in their laboratory facilities. That's the reason why we often see that these core plugs that are taken from core data have about the same size. So that's an important concern. And how the operating companies, when they are drilling the well, know that is right now the best time to start coring. Because remember, it's very expensive to core long intervals of the well. Very expensive because we have to pull out the drilling subs and we have to set at the drill bit a new coring instrument. It's a core barrel. So it's not the same drill bit. And then that core barrel goes through the well and it acquires these cylinders. We saw them in the previous presentation of 3 inches. It can have multiple sizes, but the core barrel replaces the drill bit. And then these cylindrical samples are retrieved and sent all the way to the surface. So we need to have a special procedure to core, and it's expensive. It takes time. It slows down the drilling process, so we need to know exactly when one has to core. And typically this is done in multiple ways. One is to use seismic data correlations between the drilling cuttings, so the interpreter at the well is continuously sampling the drilling cuttings to assess whether they have reached the formation that they're in, the geological formation that they're interested in producing, or because of correlations between wells or previous geological analysis, they have an expected value for the depth with these formations will begin to show up. Of course, plus and minus some uncertainty range. And this also sometimes can be done with seismic amplitude data or with vertical seismic profiles, which are the drilling process steps at some point, and then we shoot seismic waves below the well at the termination of the well to measure how far are the subsequent geological interfaces from the current location of the drilling process. So it's an anticipation of where the geological formations will be based on seismic waves, for instance. So we have a few methods to anticipate. But it's important that we anticipate because, as I said, we have to modify the drilling machinery and we have to give orders to do something else. If we miss this interval, we will miss it forever. We will not be able to retrieve these samples, unfortunately. So it's very important. It's a very precise, very tense moment when one is trying to locate these depth intervals to give the order to begin coring. So that's an important thing. So we are going to look at all of these properties from this well. This is a turbidite sedimentary system. It is from the Permian Basin. It's quite old. It's not such as the turbidite sedimentary sequences that we have in the deep water Gulf of Mexico that are unconsolidated. This sequence is extremely well consolidated and cemented. Porosities, as we're going to see, have a very interesting interval. please, you have access to this plot. We're going to look at the energy, at the variability of the gamma ray log, and we're going to compare the variability, the local maxima and local minima, with specific locations on the core samples. And we're also going to identify segments where the porosities are high and the permeabilities are high, and why at certain sections of the core interval we have maxima or minima of the gamma ray log, all of these things. So just remember that the scales are given here, the gamma ray log, the bit size, the caliper, the resistivities. As I said before, we have the super shallow, which is the blue, then we have the medium, this is an induction measurement, and that's the green, and then we have the deep sensing log, which is the red. And then here we have the density porosity going from minus 10% to 40% in sandstone porosity units. Same for the neutron porosity log. And please note that the neutron and density porosity logs are somewhat separated, even though the dominant matrix composition here is quartz, and that's because this segment contains a non-trivial amount of clay. That's the reason why we have this separation, otherwise we will see better coincidence. And then we have the photoelectric factor log, and here we have the calculated gamma ray log versus the not calculated. Please remember that this calculation is done by taking away the effect of the uranium log on the gamma ray log. And then here we have the core permeability. So this is just a close-up of what we're going to see in a minute. Here's the summary. It's the same summary they have for the previous lecture. The only thing that I added to this summary is that depth match of core and logs is very, very important, and we have to do as a previous element of the interpretation when we go and look at core and logs. It is not uncommon that we have a mismatch of a few, even sometimes tens of feet between core and logs, so we have to be prepared for that. Also, I had some review questions from the previous session. I added a couple more of elements for these review questions based on what I did today. For instance, I asked how are well logs and core samples typically matched in depth. I explained that, and why are there standards for logs got from core samples. Standards for size, that's what I mean by this question. Standards in terms of size of blocks that are used for core samples. And can one retrieve core samples from wells after the well was drilled? Yes, there's a possibility to do that. It's very expensive, and essentially what we do is we send an instrument after the well was drilled before the casing is placed. In fact, sometimes we can do it even after the casing was placed, and then it's an instrument that drills through the walls of the well. So you have the well, you send an instrument, and the instrument takes core samples from the well, from the borehole wall, by drilling through a size and retrieving through a cylinder all these segments. The only problem is that the core samples are now going to be in a specific direction, but we can anticipate the azimuth of the location of the sample. So we can do that after the well was drilled, but it's more expensive, and potentially the core samples are a little bit more disturbed than what they would be if we would retrieve cylindrical core samples, whole core, that is to say. And I'm also asking here, what is the depth range? How is the depth range core interval ascertained while drilling the well? And I mentioned that. With that said, I just want to reiterate that I send my heartfelt thanks to Charlie Cairns, Dottie Larson, Jerry Lucia, the Bureau of Economic Geology of the University of Texas at Austin, and the Hildebrand Department of Petroleum and Geosystems Engineering. Thank you. Now let's go to the core log facility. Now we're going to look at a turbidite sedimentary sequence. This is a very old turbidite sedimentary sequence. It's located in the Permian Basin, is in Dawson County, Texas. Hillier Oil and Gas. The well is called Brown Trust number 1. And it's interesting because we have the well logs for this sequence, but I wanted to walk you through the various sections of this very old turbidite sequence that has been highly cemented and consolidated, or consolidated and cemented in that order. But please take a look at the variability of rock properties. I'm showing my pen just for scale here, but we have segments that have laminations, segments that are clean, then almost segments that are pure shell. So we have the great variability between transitions from a pure shell to intermediate variations because of very thin lamina of shell going through here. We call it the laminated siltstone. Also, please note that some of these rocks break very nicely between some transitions of the rocks. We also see presence of clasts. In some situations, we also see presence of bioturbation, some clasts, or some elements that are produced by the diagenesis of the rock. The porosities of these rock oscillate anywhere between 10 to 20%. And we see these holes that you see here were segments, plugs that were taken from the rock itself to perform laboratory measurements. And those are the ones that we have here also to show you. And but please note that within very short distances here, we have great variability of properties. So this is a highly variable turbidite sequence. It produces hydrocarbons, gas in this case, and we have also segments that are more thickly bedded turbidites, probably because we're getting close to the channel of the turbidite systems. But I want to emphasize that this property is very greatly important in terms of porosity and permeability. That's what we visually see here. We continue to walk through here. There are segments that are thicker, more homogeneous, but those segments are very short in distances. We come to different portions of the rocks, more laminations as we see here, and then we also come to a better section of the rock. It turns out that this section of the rock where I have my pen going through here is probably the best section of the rock because it has the best petrophysical properties, the best storage and flow properties, the highest permeability. In fact, the highest permeability takes place at the bottom here. That's where we have two plugs, where we have the largest grain sizes and also the largest porosity. So that's the best flow properties. But if we continue to walk through these rocks, we're going to see that there are other segments that are homogeneous, but we also have segments that are laminated. This all through the history of time. Please note that these rocks do not form instantaneously, so we're looking to understand these laminations very commonly found in turbidite sedimentary systems. The laminations will have a great impact not only on the flow and transport property, storage and transport properties of these rocks, also on the electrical properties, in the density of the rock, in the neutron response of the rock, in the sonic response of the rock, in the mechanical properties, elastic properties of this rock. We can do magnetic resonance as well, and we will see different values going through here. So this is very important. That's the exercise that we normally do when we do core log integration, is to understand the variability of the rock properties because of the underlying genesis and diagenesis of these sediments. And then there are segments that are obviously more organic rich, that these shells have organic material, and that has to do with the cycles of sedimentation that gave rise to this turbidite system. We in some cases were in the center of the channel, sometimes were in the crevasse place, in the levees, etc. All of this is preserved in history because of clasts, mud flows, variability of grain sizes, sorting. All of those properties are extremely important. Look at this very nice segment of shell, almost a pure shell, indicating here. And then we continue to navigate through this beautiful core, and we identify more and more laminated systems. Over here, different segments of the rock. This rock is, I'll tell you in a second what the porosities and permeabilities are. And then we see another segment of organic shell, more segments with laminated properties, very few segments that seem homogeneous. So all in all, we're looking at about 3 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're looking at about 40 feet of core. And within 40 feet of core, you can see the tremendous variability of petrophysical properties that we have here. Now let's look at the logs. The well logs that we have here are shown as follows. So at the top, let me show you this is the brown trust, and then we have the depth, 7,600 feet. Then we have the gamma ray log over here. Then we have the resistivities, the deep sensing resistivity log. The scale goes from 0.2 to 2,000. Then we have the medium resistivity and the super shallow resistivity. And then we have the density neutron logs and sensing porosity units going from minus 10% to 40%. So we have each one of these tick marks is 10 porosity units. So this will be 0, and this will be 10, and this will be 20 PEF. And then we have the core porosity, and then we have the corrected gamma ray log and permeability for cases that we have the log. But what is important is that obviously if you look at the gamma ray log, what we're seeing here is the manifestation of the averaging of properties, where the averaging means when you have laminations and not laminations. So local minima in this example are going to have to be correlated with segments that are relatively clean. For instance, 7660 will be a segment that is relatively clean. And that segment happens to be somewhere out here, relatively clean. Okay, so that's a local minimum of the gamma ray log. So that's where we have core data, by the way. So I'm guiding myself through the section that has core data. That's where we have this core. And then we have other segments that are local minima, 76, 75. Actually, each one of these is 4 feet. So please take that into account. But you can actually trace the local minima and local maxima. For instance, here, that would be presence of mostly a shell that would be about 76, 64. And that segment is this segment over here that we see a considerable amount of shell. That's where we see the local maximum. So you can see how these cycles, the cyclicity that goes between local minima and local maxima of gamma ray correlate extremely well with the volumetric concentration of shell in these laminations. And there are segments where, like in this example, please note that the permeability, the scale goes from 10 to the minus 2 to 100 millidarcies. So the maximum permeability that we have here is 100 millidarcies, and that happens to occur right here. That's a segment that has the highest permeability. It's also, in this example, it has the highest porosity. Please look at this. That's where we have the highest permeability, the highest porosity. Is not the lowest value of gamma ray log, by the way. The lowest value of gamma ray log takes place directly above it, somewhere about here. But that's not where we have the best petrophysical properties. That's where we have. And so the relatively low values of resistivity that we have here are because of the relatively high values of porosity. As I indicating this, it would be 0, then 10, 20. So we have a porosity of 20% and a permeability of about 100 millidarcies. That's what happens here. So as we move down in the sequence, please remember the values of the scales here. We begin to see values. We have a local maximum of gamma ray log. And the question is, where is that happening? And it's happening right here where we have this segment 7682, this segment has a relatively high concentration of shell, and that's precisely where we have this local maximum of the gamma ray log. So please look, see how this transition is actually somewhat discontinuous over here, but the log, because of the averaging that is implicit in the measurement, we're looking at a longer transition over here. And then as we move along, then we see at 7700, we see another 7700, we see another relatively high value of gamma ray log. Now you can also look at the features that we have here going through these core. It's very clear from the analysis that we have laminated systems typical of a turbidite. Please note that the degree of variability that we observe on the core is much higher than the degree of variability that we see in logs. In logs we can assess variability from the gamma ray log, and that gives us an indication of the energy of the environment, but as you know, the gamma ray log has a volume of investigation, and that volume of investigation is not nearly as fine to describe these variabilities and laminations, and that's the reason why when we look at logs, we have to look at them from the viewpoint of effective medium theories, that is, average property theories that have to do with either scalar phenomena or vector-driven phenomena. And here we see a beautiful boundary. Then we come across, these are the typical holes that are left after a plug is taken to perform laboratory studies of core porosity and core permeability. And then we have more of the same going. Please see the degree of variability. Sometimes we even have bioturbation marks, extremely high variability. Certainly much more than we can see on the well logs. Please note that we have here 20 feet. The sample interval here is ½ foot, and the size of this core, as you can see, this pizza box goes for, in this case, 9 feet. That's what this box is telling us. This is in Dozen County, Texas, 9 feet. So we have 9 feet of core. So 9 feet will have 18 samples for the well logs, and that will be 9 feet will be about what I'm showing here with my fingers. So 2 of these tick marks are 8 feet, 9 feet is slightly longer than that, but that can give you an idea of the variability that we can see in the logs. So essentially the logs are taking a very rough average of things. Here the resistivity logs are extremely constant. Porosity, as I said, varies between 10 and 15 porosity units, and 15 and 20 porosity units, and then we have great variability on permeability. In fact, if you look at 7680 is where we have the highest permeability, and if you look at the sections with the highest permeability, they will be somewhere along here. So there's possible that also we have a depth shift in between the core and log, and that's important that we always pay attention to that variability. Please look at the great variability that we have here in laminations. That's an indication that within very short distances we have variability of grain sizes, laminations, all of these because of the way the sediment was deposited in the system of a turbidite sedimentation process. And according to the well logs that we have here at 7677 is where we have the maximum permeability in this core section in this well, and that happens to be right here. And this is precisely the portion of the rock that exhibits the largest grain sizes, the more homogeneous structure. So it's important actually to see how laterally continuous this segment of the rock is when we try to understand variability, and if this has hydrocarbons, is how to produce the hydrocarbons. I want to mention that this is the turbidite sequence in the Permian Basin. It's probably the Bone Spring, and as I mentioned, this is in Dawson County, Hillier Oil and Gas, and the well is called Brown Trust. And then we can continue to go over these logs, and I just want to show you how there are places where the gamma ray log has a peak, for instance right here, and that peak coincides with the presence of this shale right here. That's what it and often you see that the thickness here is much smaller than when shown on the logs. I also want you to see that there are segments here that are clearly very highly laminated, like this one here, and that's a reflection also of the situation where one has to use a shell laminated system to be able to calculate properties. Same here. And we go on to different sections that are more argillaceous, more clay concentrated, and obviously the gamma ray log is going to give us higher values. It's also very important to pay attention to these from the viewpoint not only of grain sizes, shale laminations, but also from the viewpoint of elastic mechanical properties, because the sonic logs, P-wave velocity, shear wave velocity are also going to give us an indication of the variability. And this concludes the section devoted to core log integration of clastic sedimentary sequences. Let's go now for a similar exercise for carbonate sedimentary sequences. Thank you and all the best.